In the last video, we had a bit of an overview of energy, and at the end I mentioned that one of the ways that energy can be transferred in or out of a system to the environment is via work. So to that end, we'll go ahead and define the work that a force does on an object. So the first key thing is that work is done by forces on objects. It's also the result of a force being applied through a distance. Later in a few video series, we will take a look at another quantity where we talk about forces being applied at a distance. That quantity is called torque. But here we are looking at the effect of a force being applied through a distance. And the definition of work is that it is the parallel component of a force multiplied by the displacement. So, for instance here, let's say I'm applying a force like so, and I have an object displace like so. The piece of the force that's going to count for the work is the part that's parallel to the displacement, this bit right here. And this is because we keep in mind that the kinetic energy of an object depends on the speed. And we remember that only parallel components or anti-parallel components of a force can affect the speed, because that will give you parallel or anti-parallel components of acceleration. So thus the speed can change. Perpendicular components of a force will be responsible for changing the direction of a thing, but not the speed. So we won't care about these for now. Later, when we get to rotational dynamics, we'll worry about those. Now, in this particular example, there must be more than one force acting on the object in order for it to keep displacing in the direction that I drew it. But this would be the work that this particular force does. So if we go and look at the units, if you take a Newton and you times it by a meter, you'll get that, again, the units are joules. And it's very, very important to write joule and not Newton meter. Newton meter is a unit of this quantity called torque that I'm making reference to, and it's a different physical quantity that has the same physical dimension. So in order to keep the two straight, the units of work are joules, and the units of torque, when we get to that point, will be Newton meters. So when you're doing your unit analysis, you do need to ask yourself, when you get newtons times meters, you have to ask yourself, okay, is this work? And if it is, you need to replace that with a J for joules. Okay, and work has a sign, because if, as I drew it here, the parallel component of force is pointing in the same general direction as the displacement, that would be a positive sign. And here, this would be causing the object to accelerate in this direction. So we would be picking up speed. So positive work will correspond to object picking up speed. And on the other hand, if our force is pointing in an opposite-ish direction relative to the displacement, that would mean that the object is slowing down. So for instance here, this would be if the displacement of my object is to the right, and I'm applying a force, let's say up and to the left here. In this case here, my component F parallel is anti-parallel to the displacement. So it's trying to slow the thing down. And that will correspond to a negative work. Now, I should say that this is what this particular force is trying to make the object do. It's trying to either make it pick up speed or slow down. But we could have multiple forces acting, and it turns out in that case, to figure out the net effect of all the forces, all we have to do is add up all the work. So that's one way that, okay. So with that, we're ready to get to what I'd like to call the first version of the work-energy theorem. So also people call it the work-kinetic energy theorem. So let's go with that. So in my approach here, I'm only going to look at this for a force that's directed either parallel or anti-parallel to the displacement. We're going to constrain everything to one dimension. And then I'm just going to assert that a more careful treatment will work for general forces pointing in general directions and in 2 and 3 dimensions. So with this, we can start by defining the net work being done on object, and observe that that would be the net force acting on the object times the displacement. This makes sense because the net work would be talking about how a force is overall attempting to either increase or decrease the speed of the object. And again, here we're only looking at things in one dimension, so the acceleration will be due to the net force. So it's a sensible enough definition. We can follow this through from Newton's second law of motion. And remember that this would be equal to mass times, we'll say, the x component of acceleration here. And translating back to the definition of displacement in one dimension, that would be the final position x minus the initial position x naught. And then we recall from our study of kinematics that this looks like, this bit right here looks a lot like the missing t equation, and you'd be correct. We recall that v squared minus v initial squared is equal to 2a times x minus x naught. Okay, so I can divide through by 2 and get that our quantity ax, x minus x naught, is equal to 1/2 v squared minus 1/2 v naught squared, and I can substitute that in up here. So that will give me, whoops, that the net work being done will be equal to, if I times through by m, 1/2 mv final squared minus 1/2 mv initial squared. And we recall from the previous video that this is what we found to be the kinetic energy. So we will define this to be the final kinetic energy and this to be the initial kinetic energy. So we can write that the net work done on an object is equal to the change in the object's kinetic energy. All right, so let's do a few examples to see how we might be able to use this. And I'll warn you that usually this first version of the WorkEnergy Theorem, there are times where it's more useful than other approaches, but right now it's, for most problems you're going to look at, it's probably going to be about as much effort as other approaches. Once we define potential energy and we get to the second version of the WorkEnergy Theorem, that's when things are going to become computationally a lot nicer. But let's work through a few examples just to get a feel for it. So one of my big references is always just let's imagine dropping a rock. So my rock is initially at rest. Let's say we are falling through a height of 10 meters. So this means that the rock is going to displace downward. (10 meters). I'd like to know how fast is it going just before it hits at the end of its fall. Well, to figure out the work, so here, let's look at the forces. There's only one force, gravity. We're neglecting air resistance. So to figure out the work, what I like to do is I will draw in the force, and I will draw in the displacement, and then I will figure out the parallel piece of it. In this case, they're pointing in the same direction. So we can say that the work done is F parallel D. And we can write that as F times D times the cosine of the angle between these. In fact, that's often the more useful way to put it. So this angle theta would be the angle between the force and the displacement. This would be the force times the displacement times the cosine of 0 degrees. Because they're pointing in the same direction, cosine of 0 is 1. So the force of gravity is equal to mg, so this is mgd. All right, so now the net work is equal to ke final minus ke initial, so this is 1/2 mv final squared minus 1/2 mv initial squared. And V initial is 0, so the initial kinetic energy is 0. All right, so equating the net work, because all we have is the work done by gravity here, will be mgd. That'll equal 1/2 mv final squared. So it turns out we did not need to know the mass of the rock. If I times both sides through by 2, take the square root of both sides, I get that V final. So square root of 2 GD, which is a result we saw before from doing kinematics. So this is square root of 2 times 9.8 newtons per kilogram, which we can go ahead and recast as meters per second squared, times 10 meters. This works out to be 14 meters per second. All right, let's maybe do a slightly more complicated example. Let's try doing an Atwoods machine. So remember, an Atwoods machine is a pulley which we're still making massless and ideal, and the strings are all perfect and ideal. So let's say here that M1 is 5 kilograms, and M2 here is 10 kilograms. And we'll say that the 10 kilogram mass has fallen by 1 meter. So similarly, the 1 kilogram mass will have gone up by 1 meter. I'd like to know how fast at this point are the masses going if initially it was at rest. Okay, so here the trick is to cleverly define your system. And here we can isolate out the system better if we just make the whole Atwoods machine the system. Then the only two forces that are external to the system are the forces of gravity acting on the two masses. And then we don't have to worry about the work done by tension on the masses. If you were to make the system, if you were to say look at two systems, you'd have to figure out the work done by tension, but it would turn out that they would be opposite signs to each other. Or no, I take it back. Yeah, they'd be opposite signs to each other. But we can finesse that all out by just making the tension internal to the system, and then it doesn't matter for energy transfers in and out of the system. So, all right, let's go with our recipe here then of saying that the net work is equal to delta KE. So this will be KE final minus KE initial. And initially both masses are at rest, so the initial kinetic energy is 0. Now here, let's work out the work done on each of the masses. So the work done on mass number 1, well here the force of gravity is pointing up, but the let's try that again. The force of gravity on the mass is clearly pointing down, but its displacement is up. So this is going to mean that there's a 180-degree angle between the two masses. So we'll say this is W1 plus W2, and we'll worry about the kinetic energies in a moment. So the work done on mass 1 will be the force of gravity on mass 1 times the displacement times the cosine of the angle between them, which in this case is 180 degrees. Cosine of 180 is -1. All right, now for mass 2, we have the force of gravity acting on it down, and it's also displacing down. So this will be FG2D cosine 0. Cosine of 0 is 1. All right. Let's look at this kinetic energy term. Now we've got two things that are moving, so we have to write in the kinetic energy of each of the two things. So this will be 1/2 m1 v squared plus 1/2 m2 v squared. And again, we don't have to worry about the signs of v or anything like that, because all that matters is the speed. All right, so let's go ahead and put this together. We'll get m1 gd with a minus sign in front, plus m2 gd, that's just substituting in mg for each of the f's, is equal to 1/2 m1 v squared plus 1/2 m2 v squared. All right. So we can combine this around a little bit to try to make it a little prettier. Here, these both have a 1/2 and they both have a v squared. So I can group out a 1/2 and I'll have m1 plus m2. Actually, for symmetry's sake, I'm going to write as m2 plus m1. And then I can pull out a v squared here. And then here, there's a g and a d I can pull out. I can write this as m2 minus m1 GD. All right, now if we multiply through by 2 and divide by what's in the parentheses here and take the square root, we get that V is equal to the square root of M2 minus M1 GD over, with a 2 in front, over M2 plus M1. Okay, so then it just remains to put in the values and away we go. So this will be square root of 2 times 10 kilograms minus 5 kilograms times 9.8 newtons per kilogram, which again we can recast as meters per second squared, 1 meter for our displacements, over 10 kilograms plus 5 kilograms. Alrighty then, when you punch that through on your calculator, you'll get 2.56 meters per second. So certainly when you're looking at this problem, you might go, I think kinematics is probably easier, and you'd probably be right, but at least physics is consistent and you can do the same problem more than one way and get the same answer. Here though, I would submit that this is maybe slightly easier than doing the dynamics and the kinematics, because if we did this at dynamics and kinematics, remember that we had to make the two masses separate systems. We had to equate the tensions, and we had to solve for the tension and eliminate the tension. It was an algebra nightmare. Here, by just worrying about the energy transfers, we can make the whole Atwoods machine our system. That makes the string internal to the system, and we don't have to worry about the work that the tension is doing on either of the masses. That gets baked into the cake automatically. So that saves us a bunch of effort. So now instead of doing quite a bit of algebra, we have just a couple lines here before we finally get to our answer. And that's always the game with these conservation principles. You can always solve everything with Newton's, in mechanics, with Newton's laws of motion and our kinematics relations, and quite possibly an awful lot of computational effort. Here, what we're doing is we've identified that since this quantity energy is a special quantity, and we can do good bookkeeping on it, it's a lot easier for us to just calculate the work being done on it and get an answer. Once we define potential energy, we'll be able to make this problem go even faster. So far, we've taken a look at forces that are conservative. Gravity is conservative. And so far I've said, but what about friction? Well, we can take that into account now. So let's go revisit a problem that we had before. So let's say we've got a block here, mass M. No, I'm not going to say what the mass is, it'll cancel. Initially moving at 10 meters per second, and it'll slide to a halt. The coefficient of kinetic friction between these surfaces is 0.25. Now what I'd like to know is how far did the block travel? So what's the displacement? Okie dokie. So to do this, we're going to have to do a little bit of dynamics. We can't completely escape Newton's second law, because if we just go ahead and go for the jugular on this, we can say, well, if I draw my free body diagram for this, I have the normal force up, I have gravity down, and I have kinetic friction opposing the motion. So if I figure out the work done by the normal force, that doesn't seem too bad. That'll be, if I draw in the displacement here, there's my displacement. The angle between the normal force and the displacement is 90 degrees. So the work done by the normal force will be equal to the normal force times the displacement times the cosine of 90. And cosine 90 is 0. So sorry about that. So the work done by the normal force is 0 here. All right, how about the work done by gravity? Turns out to be the same deal. The angle between them is also 90 degrees. So this will be the force of gravity times the displacement times the cosine of 90 is again 0. Again, this makes sense because forces that are perpendicular to the motion can only ever attempt to change the direction of motion of an object. They can't change the speed. So then you're left with saying, okay, what's the work done by kinetic friction? Well, that'll be the force of kinetic friction times the displacement, cool, times the angle between them. And here's where we have to be careful. The angle between them is 180 degrees. So we'll have to write in cosine 180. And cosine of 180 is -1. So we can write this as minus fkd. Now here's the problem. To try to take this further, we have to go to our model of friction and say, okay, we know that the force of kinetic friction on anything is always equal to the coefficient of kinetic friction times the normal force. Crap. This means I still need to know the normal force. So we can put this on pause for just a little bit, and we can still use F net equals ma. So we're going to have to resort back to doing a little bit of Newton's second law of motion, but hopefully it won't be quite as bad as it was before. And this is because we can just take the y component of it. So then in the y direction, our force, the only force we have heading upward is the normal force, and it's all of it. The only force we have acting down is gravity, and it's all of it. And this will equal the mass times the y component of acceleration. So just pause and ask yourself real quick, what value should I put in for the y component of the acceleration of the block? Pause and I'll get back with you. Okay, so the correct response there is that the y component of acceleration is 0. This is because the block is neither levitating off of the surface, nor is it crashing through it. But anyway, this will tell us that the normal force is equal to the force of gravity, which is equal to mg. All right, so now notice this, we don't need to worry about doing Newton's second law in the x direction. We can just go ahead now and take our expression for the normal force from just looking at the y component and get the work done by kinetic friction now. So the work done by kinetic friction will now be minus mu k mg, and then we had the d for the displacement. And since the other two forces did no work, this is also the net work. Okay, so now we can say that the net work is equal to KE final minus KE initial. And since the block ended up at rest, the final kinetic energy is 0. So this will be minus mu K mg d equals minus, from the minus sign there, 1/2 mv initial squared. M's cancel, which is a good thing. Minus signs cancel. And we get that d is equal to v initial squared over 2 mu k g. Okay, so that's going to be 10 meters per second, right? yep, it's going to be 10 meters per second squared over 2 times 0.25 times 9.8 newtons per kilogram, which we can recast as meters per second squared, to yield 20.4 meters. Okay, there's a couple other concerns that we have to take into account, and that is, what if the forces are varying? In this case, what you'll have to do is make a, say if the motion is happening in the x direction, you'll have to plot the x component of the force say it looks like this, as a function of the position, and then you'll have to find the area under the curve. So for what we're doing here, you'll always be able to do this by breaking things into triangles and rectangles and stuff like that. But if it's more complicated, then you would have to use the methods of calculus to determine it. And the other thing that you'll run across, we've already touched on this with the normal force and gravity in the block sliding example that we just did, is let's say you've got a centrifuge. So we've got a sample here at the end of a rod, and it's going around in a circle like so. Well, in this case here, it'll be the tension in the rod that's what's making the centrifuge go around in a circle. And if we're going at a constant speed, say here the velocity is like this, the velocity and the tension are perpendicular, and they will be everywhere along here. So say here the tension would be again in toward the center circle, the velocity would be tangent to the circle, again it would be perpendicular. So here if a force is always perpendicular to the velocity, the work done by that force is 0. So, all right, so in the next one we will define conservative forces and further develop the idea of potential energy. So catch you in the next video.